Welcome to the lecture on game theory module 2. In this module, we will study dominance principle. By using this principle, we will be able to reduce the size of the pure matrix. Also, we will study in this module some methods like arithmetic method, algebraic method and graphical method for solving some game problems. Let us define what is the principle of dominance. The principle of dominance states that if the strategy of a player dominates over the other strategy in all conditions, then the latter strategy is ignored, because it will not affect the solution in any way. Since each player is to select his best strategy, the inferior strategies can be eliminated. In other words, ineffective rows and columns can be deleted from the game matrix, and only effective rows and columns of the matrix are retained in the reduced matrix. For deleting the ineffective rows and columns, these general rules are to be followed. If all the elements of a row, say ith row of a pair matrix, are less than or equal to the corresponding elements of any other row, say jth row, then the player A will never choose the ith strategy. Therefore, ith row is dominated by jth row, and hence we can delete ith row. If all the elements of a column, say jth column, are greater than or equal to the corresponding elements of any other column, say ith column, then jth column is dominated by ith column. So, we can delete jth column. A pure strategy of a player may also be dominated if it is inferior to some convex combination of two or more pure strategies. As a particular case, if all the elements of a column are greater than or equal to the average of two or more other columns, then this column is dominated by the group of columns. Similarly, if all the elements of row are less than or equal to the average of two or more rows, then this row is dominated by the group of rows. Now, we will prove some important results relevant to the principle of dominance. If the ith row of the pair matrix of an m by n rectangular game is dominated by its rth row, then the deletion of the ith row from the matrix does not change optimal strategies of the maximizing player. For the proof of this theorem, let us suppose that A and B be the row and column players respectively of a rectangular game, whose pair matrix is Aij m by n. We are given that Aij is less than equal to Arj for j equal to 1 to up to n, and I is not equal to R. And for at least one j, Aij is not equal to Arj. Let capital Y star equal to Y1 star, Y2 star up to Yn star be an optimal mixed strategy for the player B. Then from equation 1, we have sigma aij yj star, j is varies from 1 to n, is less than equal to sigma arj yj star, where j varies from 1 to up to n. That is, we can write E ai y star is less than E ar y star, where ai and ar are the ith and rth pure strategies of A. If V be the value of the game, then we have from above V should be greater than equal to E ar y star, which is greater than E ai y star. Let x star equal to x1 star, x2 star up to xm star be an optimal mix strategy for the player A. And if possible, let us suppose that xi star is greater than 0. Then from the relation 2, we have xi star v is greater than xi star e I y star. Again, since x star y star is the optimal solution of the game, we have v equal to E x star y star, which is equal to summation x k star E a k y star, where k varies from 1 to up to m, and this can be simplified as xi star E a I y star plus summation x k star E a k y star, where k equal to 1 to up to m, but k not equal to I. Since xi v is greater than xi star E a I y star, this expression can be written as less than of xi star v plus v into summation x k star k equal to 1 to up to m and k not equal to I, which is equal to v into sigma xi x k star k equal to 1 to up to m, which is equal to v, since sigma x k star k equal to 1 to up to n is equal to 1. Sum of the probabilities is equal to 1. This contradicts our assumption that xi star is greater than 0, hence we should have xi star equal to 0. Thus, deletion of ith row does not influence the optimal solution. Now, we would like to demonstrate this principle for an example. The first table in this slide shows the pair matrix for player A. Player A has 4 courses of action and player B has also 4 courses of action. Now, we see that columns 1 and 2 are dominated by column 4, because all the values of the column 1 and 2 are greater than the corresponding values of the column 4. Hence, columns 1 and 2 can be deleted. The reversed pair matrix is shown in the next table. Again, in this revised pair matrix, we see that rows 1 and 3 are dominated by row 4. So, rows 1 and 3 can be deleted, and thus we ultimately get a pair matrix in 2 by 2 form. And this 2 by 2 pair matrix can be solved by some other method. Since this pair matrix does not have a saddle point, so we have to use mixed strategies for the player A and B to get the optimal solution. Now, we will define some method called arithmetic method for solving a 2 by 2 game. The algorithm for this method is as follows. In step 1, find the difference of the values of cells 1 1 and 1 2 of the first row and place it against the second row of the matrix. Then find the difference of the values in cells 2 1 and 2 2 of the second row and place it against the first row of the matrix. In step 3, find the difference of the values in cell 1 1 and 2 1 of the first column and place it below the second column of the matrix. Similarly, find the difference of the values in cells 1 2 and 2 2 of the second column and place it below the first column. So, then in finding these differences, we should always consider the positive values. That means, we will ignore the negative signs. This table shows the differences which can be obtained for a 2 by 2 pair matrix, and the probabilities for moves A 1 A 2 B 1 B 2 can be obtained as B 2 1 minus B 2 2 by B 2 1 minus B 2 2 plus B 1 1 minus B 1 2. This is the probability for the move of A 1. Similarly, the other probabilities can be obtained and the value of the game finally can be obtained. So, we now define this method taking an example. The slide shows that the pair matrix for the player A, and we find the differences for the row 1. Row 1 difference is 1 minus 5 is equal to 4, because we ignore the negative sign and we put it the result in the corresponding to the row 2. Similarly, for the difference 4 minus 2, we put the result in corresponding to row 1, and then similarly with differences of the columns 5 minus 2 equal to 3, we put it in the first column, and then 1 minus 4 which is equal to again 3, we put in the second column. So, since we consider here odds, sometimes this method is also called odds method, and from these odds or differences we can find the probabilities for the actions of the player A as well as the player B with some probabilities. That is, we are able to get the mixed strategies for the player A as 1/3 and 2/3, and for the player B as half and half. Now, we will define another method called algebraic method. Let V be the value of the game given by the pair matrix Vij m by n. That means, we are considering a pair matrix of order m by n, and Pi's as the probabilities for the action to be chosen by the player maximizing player A, and Qj's j equal to 1 to up to n be the probabilities to be considered for choosing the actions for the player B, and these probabilities are shown in this slide along with the P of matrix for the player A. Now, the expected gain of A when he uses his I strategy and B uses his J strategy is sigma Aij xi. As A expects at least the value V, the value of the game, which is the value of the game, we should have summation Vij Pi I equal to 1 to up to m must be greater than or equal to V for j equal to 1 to up to n, where sigma Pi I equal to 1 to up to m is equal to 1 and Pi's are all non-negative. Similarly, for the expected loss to player B, we should have sigma Vij Qj should be less than or equal to V, where for all I equal to 1 to up to m, and summation Qj equal to 1 for j equal to 1 to up to n, and Qj's are all non-negative. To get the values of Pi's and Qj's, the above inequalities are considered as equations, and these equations are then solved to get the mixed strategies. Let us take an example. Find the value and the optimal strategies for two players of the rectangular game whose payoff matrix is given below. Here we have three strategies A1, A2, A3 for the player A and three strategies for the player B1, B2 for the player B, that is B1, B2 and B3 are the three strategies, and the corresponding probabilities for the strategies A1, A2, A3 are P1, P2, P3, and for the strategies B1, B2, B3 are Q1, Q2 and Q3. First, we notice that the game does not have a saddle point. Also, this game cannot be reduced to a 2 by 2 game by the property of dominance. Hence, this game can be solved by algebraic method. Since P1, P2, P3 and Q1, Q2, Q3 are the optimal probabilities for the mixed strategies for the player A and B, and V is the value of the game, for the player A we have these relations, and then for the player B we get the relations as given in the as shown in the slide. In order to get the values of P1, P2, P3 and Q1, Q2, Q3, we consider only the equations and solve for P1, P2, P3 such that P1 plus P2 plus P3 equal to 1, and similarly we find the values of Q1, Q2, Q3 so that Q1 plus Q2 plus Q3 equal to 1. And finally, we get the mixed strategy for the player A as 6 by 13, 3 by 13 and 4 by 13, and the optimal mixed strategy for the player B as 6 by 13, 4 by 13 and 3 by 13, and the value of the game to the player A is minus 1 by 13. It should be noted that if one of the inequalities is a strict inequality, then we apply trial and error method to find the solution of a set of equations with a few strict inequalities, but this method is quite lengthy. Here we state two theorems which are the direct implications of the duality theory and which will make the computation easier. If for some j equal to k, there is a strict inequality, say V1k P1 plus V2k P2 plus dot 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 Vmk Pm is greater than V, then the corresponding value of Qk should be equal to 0. Similarly, if for some I equal to r, there is a strict inequality, say Vr1 Q1 plus Vr2 Q2 plus dot 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 plus Vrn Qn is less than a V, then the corresponding value of Pr should be equal to 0. Another result, if one player's optimal strategy consists of exactly r strategies with non-zero probabilities, then the optimal strategy of the other player will also involve r pure strategies. Until now, we have discussed dominance principle, and we have also seen how the size of pair matrix can be reduced by using dominance principle. We have also discussed some method like arithmetic method and algebraic method, and applying this method, how can we find the solutions of game problem. Let us now define graphical method for solving a 2 by n game. This method is applicable to only those games in which one of the players has two strategies only. Here we will consider the player A, which is the maximizing player, who will have two strategies. Let the probabilities of the two alternatives of player A be P1 and P2, where P2 equal to 1 minus P1. Then A's expected payoff for each of the pure strategies of V is Ej P equal to A1j P1 plus A2j P2, which can be simplified as A1j minus A2j P1 whole into P1 plus A2j, where j equal to 1 to up to n, and Aij's are the elements of A's pair matrix. Then we draw the line segments for the expected payoffs between two vertical lines unit distance apart. These line segments represent A's expected gain due to B's pure move. For the player A, the objective is to maximize the minimum expected gain. So, the highest point of the intersection of the gain lines in the lower envelope represents the maximum value of the game for player A. The two strategies of player B corresponding to those lines will pass through the maximum point, and this helps in reducing the size of the game to a 2 by 2 game. Let us consider an example of a 2 by n game and see how can we solve this game problem graphically. We will first find A's expected payoff for each pure strategy of the player B. B has 5 pure strategies, B1, B2, B3, B4 and B5, whereas A has 2 pure strategies, A1 and A2. So, we calculate A's expected payoff for each pure strategy of the player B. Thus, for the pure strategy B1, we have A's expected payoff E1 equal to minus 13 P1 plus 8, and then similarly for B2, the A's expected payoff E2 is equal to 5 into P1 minus 4 into 1 minus P1, which is equal to 9 P1 minus 4. And similarly, we calculate A's expected payoff for B's pure strategies B3, B4 and B5. Now, we consider two vertical lines unit distance apart. This line indicates for A's pure strategy A1, and then this line indicates A's pure strategies A2, and the line segments are the expected payoffs when the player B takes one of his 5 pure strategies. And the figure shows that the lower envelope by the shaded region and the maximum point as indicated in the figure by the point P, which is the intersection of the line segments B3 and B1. Thus, the 2 by n game is reduced to a 2 by 2 game, in which player B will consider only the two strategies B1 and B3, and player A will consider his strategies A1 and A2. Thus, we get a 2 by 2 game, and since this 2 by 2 game has no saddle point, we will find the mixed strategies. For this, we assume the probabilities for the strategies A1 and A2 of the player A as P1, P2, and for the strategies B1 and B3 of the player B with probabilities Q1 and Q3. So, in order to find the optimal strategy, we will consider equating the expected gains E1 and E3, and then solving for P1, which gives P1 equal to 9 by 14 and P2 equal to 5 by 14. And from this we can get the value of the game V as minus 5 by 14. Similarly, we can determine the optimal strategy for the player B as Q1 equal to 1 by 14 and Q3 equal to 13 by 14. So, this slide shows the optimal strategies, mixed strategy for the player A and for the player B as well. The value of the game is thus obtained for the player A as minus 5 by 14. We have just finished our discussion on the graphical method for solving a 2 by n game. In the next module, we will discuss the same method, that is the graphical method for a m by 2 game. So, with this we end this module.